Can you all hear me? What? Yes, thanks. So first of all, thank you very much, Jan, and also to the SimQ team for inviting me to give this talk. You might be thinking, why is the marketing guy giving this talk about AI today? I will come and explain in a couple of slides why that is. And I want to talk to you about, obviously, a very hot topic, as we've already talked about AI, obviously. And I want to talk to you how we can actually accelerate or reduce testing, maybe even in the medical field, using a new AI algorithm. Okay, so a little bit about me. Why would I even present this to you in the first place? I'm a mechanical engineer by trade, and I kind of moved to the dark side and then moved over to the marketing and sales departments. Kind of found an agency in 2022, and now it's called SimQ, kind of its marketing activities, kind of selling and marketing expertise to the public. And I've been very fortunate to also talk to some of the most well-known people in the industry, some of them from the CFD space, even Gilbert Strang, who you probably might know if you're into mathematics, also the inventor of the LSTM network, and then even Jim Cantrell, who was in the founding team of SpaceX. So really, really cool people I could connect with over the last three and a half years when I founded my podcast. So outside Jan, the handsome guy who's in the top right on my show. So yeah, also interesting discussion, which you definitely have to check out. Some of the companies we work with are listed here, and obviously also SimQ, who was kind to invite me today to talk about AI. One of the things I want to tell you, like going into this talk, is obviously I do not think that AI will substitute us or the engineers or someone else. Obviously, there will be a transformative shift happening in the industry, but I really believe that AI will be kind of more of an augmentation of existing skills for the engineer, helping them to focus more on the creative tasks, on the more important tasks. And even talking to experts now, as I've shown you in the slide before, even they say working in the field of CFD, maybe structural mechanics, or even in the testing space, they see AI more as a productivity tool rather than a substitution of existing engineers. So you don't have to worry if you're an engineer. I do not think it will substitute you, but it's more like an augmentation rather than a substitution. There's a fancy word I wanted to use, which is called intractable physics. And what that means is more or less complex physics that we deal with as engineers on a day-to-day basis. And batteries is one of these examples. Could be also fluid mechanics examples. If we talk about sloshing in the fuel tank, for example, you want to kind of predict how fuel sloshes in a tank. It makes noise, but doesn't make noise. You can kind of predict that with physics-based models, but there's already very performant AI models out there that do it way better than physics-based approaches even today. And we've proven that with the customer that I have or work with, namely Monolith. And we could also have a look at the engineering challenges. Some of the KPIs or challenges we have a look at, which is, for example, for batteries, expanding range, improving safety, but also reduce charging time. These could be transferred to, for example, the medical use case. So if you have specific KPIs or regulations that you have to follow, you could kind of transfer one-to-one to the medical space and then use these data-driven approaches to kind of fulfill these KPIs or regulations. And what we want to achieve as engineers is, for example, for batteries, obviously reducing cost and increase, hopefully, battery lifetime. And you might be thinking, what has this to do with medical or medical applications? Well, you could move this whole AI-based procedure from the automotive space over to the medical space. So how can this algorithm be used, that I'm going to present in a bit, to reduce medical testing? And the secret is basically active learning. So an active learning approach, where it's kind of a secret sauce, is kind of a combination of different algorithms, basically giving you the best results and kind of reducing tests by up to 73%. Kind of going a little bit more into detail of what I mean with intractable physics. So obviously, as we talk about engineering applications, there's a ton of variables or degrees of freedom that we have to solve. So it's very, very complicated to, as an engineer, use our own brains, which is already very powerful. But we use more or less our intuition, our gut feeling as engineers, or our experience, I would call it, to maybe look at the system and say, okay, this might work, this might not work. And also rely on the experience of maybe engineers who might have left the company already. And we talk about nonlinear physics. So if we talk about fluid flow simulation, which is highly nonlinear, and you use obviously Navier-Stokes equations and then solve them computationally to kind of solve a specific fluid flow phenomena. And especially for batteries and other applications, if you, for example, have a very highly nonlinear material model, this becomes quite complicated. And then, as you can see on the bottom left, which I already alluded to, very difficult to simulate. And especially in the case of, let's say, fuel sloshing, we have proven, for example, these microphones, you could put them in a fuel sloshing tank, you could kind of record how the fuel sloshing noise would behave in a fuel sloshing tank. So when you move it, it makes some noise. So as if you drive a car or, like, let's say, a vehicle, it wouldn't be comfortable if you hear the noise all the time. So what you can do actually with AI already is resolve kind of the frequency spectrum of this application much better, because CFD would take way too long to solve this particular use case. So what we've proven is that you can use AI to solve this case much faster compared to the traditional physics-based approach. And then last but not least, if you have unpredictable usage. So for example, worst case scenario kind of predicting these in areas which might not have been tested in the first place. And kind of one of the inspiration has been a Stanford paper or published by the Stanford researchers who have shown that you can literally reduce battery testing times from 2 days to literally 16 days, which is kind of a reduction of 98%. And you might ask yourself, okay, why did I talk about 73%? One of the reasons is that you try to have an algorithm which is also applicable to the real world. So if you have a specific dummy data set that you work with, then yes, you can achieve results up to 98%. But then if you want to make it universally usable or replicable for the real world, then you would achieve something like around 73% max, for now at least. And this was kind of the inspiration. And then kind of talking to you about some of the engineers here in the room. Might know this already. There's kind of this status quo going around how you actually test. So you could go like the hardcore mode and say, I'm going to the full factorial approach and test everything, every possible scenario that's available to me or what I want to do. Then you could do the random approach and just pick a couple of points in the design space and test those. And then you can go, as I already said, experience-based, like based on the knowledge of other engineers or maybe colleagues, or you do it even based on regulatory requirements. So then talked about this kind of certification standards that you have in the medical space. So maybe you could even use a CSV file. This is something the algorithm needs. So a CSV spreadsheet, and you kind of feed the red points in the CSV spreadsheet and put it into the algorithm. And then based on that, which is going to be the next thing, based on active learning in MTR, which is an acronym standing for Next Test Recommender, and what the name already says, it recommends next tests to run. So as an engineer, if we go back again, one slide, you could provide the algorithm with the data points on the very right side, so the regulatory requirements, and then you would say, okay, we take the iterative approach now. This is the initially available data set provided. So it could be some kind of constraints that you have from the government, from some regulations. And then the algorithm would do as, I think, based on my understanding of the data set, you should probably test in these regions. And then the engineer comes in, reviews the recommendations, which is very important. So this is not a solely AI-based approach. It is also a human-in-the-loop approach. So the engineer is still needed, kind of reviewing the recommendations the algorithm makes. And then the recommended tests are performed. And NTR, the algorithm, will update the strategy, so the exploration strategy based on the results that it has generated. And then the whole thing begins from here. This is kind of how you can basically get tests or recommendations inside of the kind of a notebook environment. If you know Jupyter Notebook, it tells you, for example, this is test 1, test 2, test 3, and so on and so forth. And what we call this whole thing is basically a TPO, so test plan optimization. So how do you have a test plan that you ideally want to optimize? Because I think a good example is if you go into a wind tunnel as an engineer. Usually, especially for electric vehicles, you would have specific rim designs. So if you have a look at an electric vehicle, they have very weird, sometimes rim designs. Obviously, to reduce drag, makes sense, right? Because you want to increase range and reduce fuel consumption. So what engineers do is they go into the wind tunnel, which sometimes costs tens to hundreds of thousands of euros per day. So you go into the wind tunnel and have to remove the rim, put another rim on, and so on and so forth. And what you can do with these algorithms is it tells the engineers, hey, what if we test maybe this rim design or maybe this rim design? And you could go in and say, okay, I'm going to pick the top 3 or top 5 of recommendations and save a lot of money in an ideal scenario. And how that works in Monolith, for example, is, as I already said, it's kind of a notebook. So you can kind of build your AI pipeline starting from data upload, then model building, and then result interpretation. And this, for example, in the bottom right, as you can see, you can probably barely see it. You can see the ranking of different tests, and then basically based on what impact factors does it recommend the test. And we can kind of summarize this in 3 words: so predict, explain, and optimize, which I think is the most crucial thing for engineers. So you can make predictions based on either a scalar value or a curve prediction. And what's really important to see is if you have a look at the right curve, you see not a single line or like a nonlinear curve. You see it more like with a confidence interval. And I think in the beginning we heard about confidence intervals. So that's very important for engineering applications to really see like in which intervals can I assume the result to be, or what can I assume what might be the worst case or the best case scenario in these cases. That also deals with uncertainty quantification in this stage. Then we have explain. Obviously, especially for clinicians and doctors, it's very important to explain the results, make them explainable, why the algorithm has decided for what it has decided for. So you would also have what you can see kind of in the middle, like based on what features it has decided to make a recommendation. So you can go back and see what of the features that you have put into the algorithm it made the recommendation, and maybe tweak and focus on these tests or maybe the specific feature that it has proposed to you. And then last but not least, optimize. So you obviously want to create an optimal design, and this is actually what this is all for. So at the end of the day, if we want to optimize any engineering system, we want to find the optimal results, and this is what this is for. We're almost at the end, so I want to show you a couple of things to kind of wrap up the discussion on the presentation. You see a couple of curves. Looks a bit confusing, but what you see on the right is in the legend you have an original table order, so original data set, a random sampling strategy, and then you have 6 recommenders. And then what it does, the algorithm, is it doesn't pick the best recommender, what we think is the best, but it uses different exploration strategies based on the data sets you have provided it with, and then gives you multiple curves, so to speak. And what we can see is, I believe it's delta. It says that delta is basically the lowest curve, so the teal one, I believe. I think it's called teal. It has the lowest error after the fewest amount of tests. So how do we interpret this in the practical scenario for engineers, or maybe we are the test bench. So if we have alpha and beta, for example, you could see that for alpha, you need half the amount of tests to come to the same conclusion compared to recommender beta. But obviously, this is just a visualization to make it more simple. So this is how we test less. So instead of 15, instead of 30 tests, we only need 15. But how do we learn more? We could fix the amount of tests and say, based on 25 tests, we see that we learn twice as much with recommender alpha with the same amount of tests compared to recommender beta. This is kind of how you can interpret it. And this was basically it. So might be too fast, but I hope it was honest. If you have any more questions in the coffee break, you can just reach out and talk to me about it.